And we'll introduce today's presenter is J.B. Scoggins. He's got his, I'll let you say where your dissertation from. Okay, that's it. That's
École Polytechnique.
Yeah. So in Paris, or Paris, and JB had a postdoc for a couple years at Von Karman Institute, right? And he'll be giving a talk on machine learning applied to entry-descent landing applications.
Thanks, Paul. Hello, everybody. Let me just pull up the slides. Awesome. Hopefully you guys can see slides on your end. All right, great. Yeah, so thanks again, Bill. So my name is J.B. Scoggins. I'm going to try and talk about sort of an introduction to machine learning today, and then I'll sort of show some examples from kind of my work here at NASA. Just to kind of add to what Bill already mentioned about me. I'm a relatively new hire, I guess, here at NASA. I think I'm coming up on 2 years, actually. But I've, I guess, been around for a long time. I think I was trying to figure out when my first internship was, and it was either 2009 or 10. So I've kind of been out at Ames and now here a fair amount. So yeah, I'm happy to be here and to give a talk. The reason I'm talking about machine learning in the first place is I did do my PhD work on coupled radiation and ablation for atmospheric entry vehicles, and then I thought I never wanted to do that again, and actually left and did a postdoc for about 3 years on machine learning and specifically physics-informed neural networks, and looked at spray modeling of all things. Realized I missed actually the EDL side of things and came back. So ended up winding up here at Langley, and yeah, happy to be here. So. Let me get started. First off, for all the interns here, happy National Intern Day. And just to embarrass my intern, I just want to quote him because actually it's a perfect lead into this talk, I think. So just this morning, Levi, my intern, said machine learning is easy, but also machine learning is hard. And so I think what he meant by that was that it's so easy with the abundance of resources online to basically put together machine learning models super fast and get results. But if you don't really understand what those models are doing and sort of what you need to kind of do to massage your data to get it to a point where you can use those models, it can be hard. So the goal of this seminar is really to try and provide a little bit of a foundation in machine learning so that you can then go pick up models and sort of hopefully kind of have a better idea how to use them. So it's a very sort of broad field. It's going to be kind of impossible to go over everything, obviously, in an hour. So instead, I just want to kind of introduce some of the core principles and some of the vocabulary so that when you see it, in the literature or online somewhere, you have a better idea of what people are talking about. And then at the end, I'll provide a few resources for self-learning, so some books and things like that I would recommend. The second goal of this seminar is really to demonstrate some recent examples, as I mentioned, kind of in my own sort of daily work here at NASA, with the goal of trying to kind of detail sort of how I would approach this sort of typical problems and how you want to think about those and how you might combine your sort of physical knowledge and intuition with machine learning principles. And then I'll also kind of detail a little bit sort of more advanced topic of Gaussian process regression and show some examples of that. All right, so let's start off with a very boring formal kind of definition. So what do we mean when we say machine learning? Basically what we're talking about, we say a computer program is said to learn from some experience with respect to some class of tasks and performance measure if its performance at those tasks as measured by your performance measure actually improves with your experience. Okay, so let's sort of break that down. So this is sort of really telling us two things. The first thing is that in order to actually have like a well-posed learning problem, you need experience, which is essentially data. You need some task at which you want to basically perform. So in our case, it's usually some sort of model prediction. And you need to be able to measure the performance of that model. In addition, the sort of second component of this is that it's only really machine learning if the algorithm can improve its performance at a given task automatically as it sees new data. So to kind of like try and help sort of distinguish between machine learning and just smart programs, I have this sort of example coming from the world of chess. So if anyone plays chess, you're probably familiar with Stockfish. That is not a fish. That is actually just the name of a chess engine, essentially, that can look very deep in all this sort of tree of all the various moves and decide what the best move is to take. And so this is normally how grandmasters used to sort of analyze different positions and learn. So its task is essentially to win the chess match. Its performance measure is how many times it wins. And the experience that it gets, so kind of the data, is actually human logic and intuition. So this is a bunch of people basically putting all of their kind of logic and intuition into a code with a whole bunch of different rules to try and understand like how to win chess. In contrast, on the right side, you have a picture from Science magazine there of AlphaZero. Well, it's not a picture of AlphaZero, but depicting what AlphaZero is, which is basically a Google AI that was able to essentially beat Stockfish after 4 hours of training. And if you look, it has actually the same task and performance measure. So it wants to win the chess match, and its performance is how many times it does that. The difference is it is an algorithm that essentially plays itself over and over and over and learns from its mistakes until it gets better. So Stockfish, while it sort of seems like a smart code, is not actually what we would call sort of AI or machine learning because it cannot automatically improve the performance given additional experience, while AlphaZero, on the other hand, can. So there's a lot of different types of sort of machine learning problems, and people like to kind of classify them into these sort of broad categories. So the first there on the left is called supervised learning. So this is basically any task where you have sort of training data that's labeled. And when we say labeled, what we mean is that you have some inputs and associated outputs. So an output is thought of as kind of a label. And so typically those kind of tasks break down into two more categories, classification and regression. In this talk, we will essentially just focus on regression because that is essentially like the kind of model prediction paradigm that we're kind of most interested here at NASA. So the next sort of broad category is called unsupervised learning. So this is actually where you have data with no labels. So you can think of a bunch of inputs with no associated outputs to some model. And there are a number of different reasons where that might show up. And you basically want to group like data points together. So this could be like images or songs or things like that. And so there's a whole bunch of algorithms and things like that for trying to cluster those into various groups. The last sort of topic is reinforcement learning. And that's a completely different can of worms. It's kind of fascinating if anyone's interested in that, but essentially the idea is you want to basically have some kind of agent, and this agent essentially takes a state of some sort, a state of itself in an environment, and any feedback that the environment gives it, and it's basically trained to, given the state and the environment, provide some action. And so the idea is that you're basically trying to get an agent to learn how to complete some task, and normally it needs to do a series of actions before achieving that task. So things like, for example, AlphaZero that I mentioned before, that is part of its algorithm, is this for reinforcement learning. So again, for this talk, we're going to basically ignore unsupervised learning and reinforcement learning, but just so you know that those are a whole other kind of field out there that you can have a look at. All right, so let's kind of get down now to what actually regression is. Regression is really nothing more than just basically trying to learn some kind of functional relationship, which we call a model, between inputs and outputs, so that we can make predictions on unseen inputs. Okay, and so you see a figure there, kind of on the right of a diagram of what I'm talking about. Generally, we would have what we call a sort of supervised learning framework, and this is just kind of sort of mathematical way to kind of precisely define what we're trying to do. So we say if we have some data set, D, which is basically a collection of input-output pairs, so xi and yi here. Sometimes these are called, they could be like inputs and targets or responses or observations. They come by different names. Sometimes the inputs are called features. So you'll hear all these different kind of words in literature. But essentially you have features or inputs over some kind of space, some domain, and there is some sort of underlying functional relationship that takes those and produces outputs. And you have measurements of those outputs. And the idea is that given some kind of model, which may have parameters in it, if it does, we call it parametric. We want to basically find the model that best underlies, that best approximates the actual true relationship underlying the inputs and outputs. And so I've written that there in this sort of notation. So this f hat I'll use to basically describe our kind of approximate model. It takes inputs x and it's parameterized by theta. And the theta star just means the sort of optimal parameters that kind of best fit f. All right, so this kind of leads to two key questions. So the first one is, how do we know if a model is actually good, much less best, right? And secondly, what do we do when our data is noisy? So in the figure on the right there, you can see that the data is kind of noisy. How do we know if that's noise, and how do we know if that's something we should be modeling? So I'll talk about these two things basically for most of the rest of this introduction. Okay, so first off, there's a lot of different kind of models out there. So for supervised learning, you know, I have some examples just listed. So you have linear models. There's a whole class of regression models called support vector machines. Gaussian processes is one I'll touch on towards the end of this talk. I think everyone's probably heard of neural networks. And so for that reason, I'm specifically not going to really talk about them, except for very briefly, because there is so much information out there. And I think it kind of overcomplicates the main purpose of this introduction. And there's another sort of class of models called decision trees, which are also very interesting. And again, I just won't talk about those today. So obviously you have to pick one. You have to pick some kind of model to start with. And you know, knowing how to choose a model is sometimes half the battle. And this choice really depends on a number of different factors. So it depends on you know, the training and evaluation cost. Is this something that's going to take, you know, months to train? Do I care how long it takes to evaluate? Is this something that has to run in real time, for example? That kind of goes into the implementation and deployment of the model. You know, is this something I'm going to have to put into a Fortran 77 code, or is this something I can like put on a cell phone or on a GPU cluster somewhere? So those are all kind of you know, things that kind of help you make this decision. How well will the model scale? And you know, do you need to actually treat the uncertainty in your model? There's a lot of other factors, but these are just some that kind of came to the top of my head. All right, and so basically to demonstrate kind of this process, I'm going to use basically linear regression, which sounds super boring, and it can be, but hopefully it'll be sort of complex enough that we can use it to you know, get through all the sort of concepts that I kind of want to introduce. So if you see the data on the right, you know, you might have some initial thoughts. Without asking everyone, I'm assuming your thoughts are something like, you know, you have some data that's generally increasing with your increasing input. It looks to be linear. It has a kind of positive slope. It looks like it has probably a negative, you know, intercept. The trend's obviously not perfect because it looks kind of noisy, or maybe, you know, maybe it's some other kind of feature that we're unaware of. But we look at that, we see this, and we say, okay, well, we're going to assume that we have a kind of linear response, and that's what we're going to use for our model. So we write down our model here, this f hat. So it takes x and two parameters, the intercept and the slope. So, okay, we can take a bunch of intercepts and slopes and make lines. So obviously, we got to go a bit further, right? Just picking up the model form isn't really enough. We want to kind of figure out how to get the best model, so the best line in this case. So in order to do that, we define something called a loss function. So a loss function is essentially how we're going to actually measure our performance on a given supervised learning task. So in general, the rule is basically you want them to be positive, and they should be kind of invariant to the data size. So if you give it more data, it's not going to affect the loss function because that could be problematic. And you want it to basically decrease. If it decreases, it's better model performance. So in other words, if you basically, can minimize it to 0, then it's like kind of a perfect model, right? So if you have some kind of continuous input space, which we'll assume, then pretty much every loss function takes this kind of general form here. So going from kind of left to right, this L of theta and F hat is what we call the loss function, and it basically is a function of the model parameters only. Note it's not a function of the inputs, it's just a function of the model parameters for a given model F hat. And it's written essentially as what we call the expectation or the expected model error over the input distribution for some given model or error model L. And so what I'm really saying there is you basically want to know, like, if I have some model and I have some input space, what's the kind of average error that you might see? And you can write this down explicitly as the integral here over basically the whole space of your input times the probability of choosing an input in that space. So that multiplied by your actual error model. Obviously, if you're kind of looking at this, you're saying, well, I don't know the distribution of my space. I'm just given some input data, right? So I don't actually really know what the true underlying distribution of all the inputs are. And I don't know the true model function, so how can I evaluate this? So typically what we do is we compute what's called an empirical loss, which is really just an average evaluated on our data set. So that might have been sort of the obvious conclusion that you would have come to anyways, but I just wanted to sort of point out like where this actually comes from. So we are interested in really modeling the sort of true expected error, but in practice we can't do that. So we have to basically make an approximation where we're sort of measuring the average error on our data set. So there are a bunch of different ways to like create these loss functions. Here are a couple common ones. So the mean squared error is one that we will use today. As you can see, it's literally just the average of the squared errors. The mean absolute error is another one that's used frequently. And then if you are dealing with probability, so let's say you want your model to actually output the probability that something is in a particular category, for example. So, the true value is either 0 or 1, so it either is or isn't. Then you could use this cross entropy loss function, which basically takes two forms depending on what your actual true data looks like. And so these are just some examples. There are many, many more of these, and the choice generally depends on the actual kind of data you have and what model you're using. All right, so let's go back to our kind of linear model. And if we choose a mean squared error loss, so basically we want to say that we're going to measure the performance in our mean squared error. That essentially leads to a linear least squares regression problem. So you can see here I've written down the loss function and I've put in our linear model. And the best model is going to be the one that minimizes this loss. And so fortunately for this simple linear problem, you can actually derive this analytically. So you'll get the values there by, of course, just taking the gradient of the loss function, setting that equal to 0, and if you solve, you can get these parameters. And so if you plug those in, you can get the actual best fit model. And so now we have that. That's cool. Great. But you can actually go a lot farther with simple linear models. So I just kind of want to point out that you can actually learn nonlinear responses with a linear model. So in general, when we say that it's a linear model, what we mean is that it's linear in the parameters. It's not necessarily linear in the inputs. All we really need to do the optimization for a linear model is that it's linear in its parameters. So we can write a kind of general linear model that you see here. So it's basically a sum over weights times some kind of nonlinear function of your inputs. And we can kind of put that in this sort of matrix vector notation here. So we can write this as basically a dot product between some weight vector and some vector of the inputs passed through each one of these nonlinear functions, and just write this compactly. And then we can write now our sort of least squares loss in this sort of compact vector notation. And then if we go through the process of doing the minimization on this sort of general problem, what you get is the sort of result there on the bottom. And so you can go through this yourself if you want, but for now, just sort of trust me, that's what it is. And that way we don't spend a lot of time on it. But you can see that it is something you can do analytically, and it's pretty easy. So the cool thing is now that we can actually do polynomial regression using our linear model. So if we take our h functions just to be powers of our input, that is a polynomial. And so we can directly, using our sort of linear notation here, we can already fit a polynomial. So if we do a third order on this data, for example, we see that we get a pretty good fit. That looks awesome, but wait a minute, if a third order is good, then why not use a 12th order, right? That looks pretty good. The problem is actually coming from two concepts, really. So generalization and overfitting. So if you use that mean squared error, it will essentially always favor model complexity over predictability. So what do we mean by that? If we just use the loss alone, this mean squared error loss, and we increase the polynomial order, so on the right you see this plot of the loss as the order increases, you see that the loss function will always decrease, right? So it sort of seems to say that to our polynomial and get a better fit. But if we look over at the left and look at the actual predictions from our models as we increase the order, you can see that there's kind of something weird going on. So as we sort of get outside of our data set and we see, this is sort of in areas where we haven't seen any data, and you look at what the predictions would be, I think, we can sort of safely say that maybe the fifth and third orders look not too bad, but I don't know, I wouldn't trust the seventh order polynomial, right? Like that doesn't really seem to fit. It's not really in line with the kind of data we have. So obviously we're missing something. And that something is being a little bit more precise about what we mean when we want to train a model. So what we really want is we want to optimize the model complexity. So in this case, it's the polynomial order to generalize well to new data without actually overfitting our current data. So if we basically fit too well our data, we call that overfitting because generally you lose your generalizability. All right, so how can we kind of fix that or at least understand it and track it? So the sort of first obvious idea that kind of comes to mind is, well, what if we save some of our data from training? We call that validation data, so that's mark those in these red squares there. We leave the rest of our data to actually train our model on, and then we compute our loss on this validation data. If we do that, we can sort of see how well our model actually fits to data it hasn't seen before. And we do this because we don't have data that we haven't seen before by nature of the fact that it hasn't been seen. So we have to use data that we do have, but it doesn't mean we have to actually give it to our model. So on the right, you can see again the black curve is the loss of the training data, and the red curve is the validation data. So as before, the training loss will continue to decrease, but now our validation data actually has a minimum around the fourth order polynomial. And beyond that, we see it starts to increase really fast. And so that's great. So now we see that, oh, actually, if we keep increasing our complexity of our model, we're going to be overfitting our data, and we're not generalizing well to unseen data. Of course, the kind of problem with this approach is that it's going to be quite sensitive to which data you've actually chosen to hold back. And so one idea that you can sort of use to try and improve on this kind of sensitivity, to sort of limit the sensitivity of that, is to compute a kind of average validation loss over a whole bunch of different choices of trained validation sets, okay? So one of the sort of simplest ways to do that is called k-fold cross-validation. And this is essentially where you take your data set, you split it into k equal parts, And then for each part, you're going to basically train the model on the remaining parts, the k-1 parts, and compute the validation loss on that part k. And once you've done that, you average all of those k validation losses together, and that gives you your cross-validation loss. If you take that idea to the extreme and set k equal to actually the number of data points that you have, then this is sort of a special case called leave one out cross-validation. And so you'll see this a lot in sort of machine learning texts, and where people are actually doing kind of this in practice. It has a couple nice features, but it's rather simple to implement. For some models, you can actually do this without having to refit everything again. So I won't go super in detail about that, but there are a lot of sort of performance improvements that you can do by kind of using this leave one out cross-validation loss. So let's have a look again at our sort of polynomial data set there and the loss curves that we get. So now I've added the blue curve is the leave one out cross-validation loss. And we can see that it has a minimum at the third order polynomial. And so this is sort of suggesting to us that the third order is actually kind of the maximum complexity we want in our model in order to generalize well to the data that we have. And so I'll point out, I didn't say this, but the way I generated that data in the first place was using a third order polynomial and adding some noise to it. And so this is kind of neat because we obviously didn't know that when training the model, and this is giving you some indication that that is sort of the true underlying function. So one other thing you can do is called regularization. And the idea here is that we want to try and basically penalize the model complexity directly in the loss function. And so we do this in order to basically improve the generalizability. So for if we go back to our kind of regularized linear least squares, so again linear least squares could also be nonlinear problems. Polynomials fit this into this model as well. So if we think about what is our least complex model, right? Well, if we make all the weights 0, we just have 0 as our output, or it would just be 0. And so that's about as as simple as it can get, right? And so we can think of as the parameters themselves, essentially, as they become more non-zero, we're increasing complexity in our model. And so, one idea you might have is, okay, well, what if we add the dot product of our weights? So that's the sum of the squares of our weights to our loss function. And just to kind of, attenuate how much of an effect it has on our loss function, we're going to multiply it by some kind of positive parameter lambda here. And so we can kind of vary lambda, and that varies how much of an effect the sum of the squares of our weights has on our loss. And fortunately for linear least squares, this also has an analytical solution for the best weights, which I've shown there. And this basically looks very similar to the previous one, where now we've just added lambda, or we've added the number of data points times lambda to the diagonal of this X transpose X matrix. All right, so just to drive home what this is doing, I've made a super simple data set here with 1, 2, 3, 4, this is 6 points. So of course, if we have a fifth order polynomial, we can exactly fit this data. And then we can study the effect of how regularization changes this. So as we basically increase lambda, you'll see that these functions become smoother and simpler. And actually, if we increase it too far, we get also this kind of odd behavior where basically if we're driving all of our weights to 0, of course, our alpha is going to start going to 0 as well. And so this is sort of not the behavior we want. So obviously, there's some kind of minimum here, right, where lambda is basically kind of right on the money. And again, you can use cross-validation to help you figure out, which is the best lambda to choose. Okay, so far we've completely neglected noise. And we might kind of want to know, is noise important? And if so, what do we do with it, right? So basically, noise in your data represents kind of uncertainty or randomness in whatever sort of process generated your data in the first place, okay? So it could be things like latent or basically hidden variables. So in other words, there's some other variable that's actually causing these discrepancies off our kind of best fit, but for whatever reason, someone didn't record that as a feature or didn't think to include that as a feature. So there's something else going on that we're not aware of. This could be something like the temperature outside, during wind tunnel testing, changing every day. Maybe this has an actual effect, but no one thought to record it, right? And so you're basically just seeing noise at that point. Another thing could just be measurement uncertainties. Whatever device you're using to take measurements, for example, just has some inherent uncertainty, and so that's going to show up in the data. And you can also have model uncertainties. So that may sound a little weird, but a lot of the data that you will get has already been kind of pre-processed, right? People have already made assumptions and done things to it before it gets to you, and so there are likely uncertainties in those processes as well, and that could further add noise to your data. So from a modeling perspective, however, this really just represents some potential error in our model because we have essentially imperfect data. We don't really have the true functional output. And so we're interested in knowing how that uncertainty actually affects our kind of model predictions. So this is not going to be a course on uncertainty quantification. That would obviously take a lot longer than we have. So I'm hoping to just kind of give a little bit of a flavor of how you might think about this. So the way this is typically thought about is we start to try and think generatively. So what I mean by that is whatever mechanism created your data, it was probably some sort of complex process, right? And we can try and model this process by approaching supervised learning in a slightly different way. So instead of looking at the model that best fits your data, we want to find a model that's most likely to generate that data. And we do that by adding some sort of noise to our model output. And we call these typically generative models. So how can we actually build a model that can generate data that looks like ours? So obviously we will accept that this isn't the real kind of generating process. We're just trying to model that generating process. But thinking this way is kind of a useful strategy. And so as I said, we're basically going to try and add some randomness to our model that mimics the randomness in our data. All right, so for going back to our linear model, let's see how we could make this generative. So we have our sort of standard linear model there. And if we add now some sort of stochastic or kind of random variable to this, then we can say that we have some basically kind of deterministic process, and then we add some noise to it. All right, so it's very simple, nothing complicated here. But note that if you do add this, then our outputs now become random as well. So our model predictions are going to become random. And I just want to mention there's kind of a subtle point. The way I'm doing this, note that the epsilon is not really dependent on our input space at all. So we're assuming that it's essentially independent of the input location. This isn't always true, and sometimes you have to basically take that into account as well. Okay, so we've just added some noise to our data. To our model. So great. Now what? There's basically two key problems that we have to solve. The first is, what is the actual probability density for this epsilon here? And then how would we fit a kind of random model to our data? So the first question I'm going to try and answer here. So in general, this depends a lot on your data and whatever knowledge you have about the actual generating mechanism. But for our purposes, you can basically just think of the key characteristics you want to model in your noise. So at the moment, the way we wrote this down is a sort of deterministic component plus noise. This really represents the kind of deviation from our nominal trend line. And that deviation could be positive or negative, and it's likely to be closer to the nominal, right, than far away. And so put all that together, and that kind of suggests like a Gaussian distribution might be a good guess. And so that's what we're going to go with. And in particular, we're going to use a normal distribution that has a zero mean. So that tends to be around the kind of trend line, the deterministic part, and has some variance sigma squared. Okay, so now to answer the second question, how do we actually fit this generative model to our data? We have to kind of understand this concept of likelihood. So again, if we have a generative linear model, then our output is going to be random. And so the output also has a probability distribution. And this is actually really easy to compute because fortunately we just have some deterministic output plus our noisy component. And so the distribution of that is simply going to be another normal distribution where the mean is now our deterministic part and the variance remains the same. Okay, and so just to clarify some of the notation here, I don't remember if this already showed up yet or not, but this notation of P, we would say P of y hat, and then this bar we say given W, H, and sigma squared. So that's essentially what we're saying there. That's a conditional probability distribution. So we're saying what is the probability of y hat being some value y hat given the values of our weights, our H evaluated on our input, and the sigma squared, our variance. Okay, so this value, this distribution, we call our likelihood. All right, because it represents how likely a model will output a particular value given the model parameters and the input location and the model variance. So we can actually now start to think about, okay, how likely would it be to generate the data set given this model, right? And so we call that a data set likelihood. And that's essentially going to be the product of the likelihood for every single data point that we have, multiplied all of these together. And that's what I've written out here. So this is some sort of new kind of probability, and this is how probable would you expect, how probable is it that using our model we would have generated this data set in the first place. Okay, so using this we can now kind of devise a strategy for actually solving for our model parameters and this variance. And this is typically called the maximum likelihood estimate. And the goal here is to basically maximize the likelihood of generating a data set with the model. So if we essentially, saying that another way, we can minimize the negative log data set likelihood. And the reason we do that is just because we want our loss function, as I said before, we want it to be positive and smaller values mean better models. And so in order to do that, we can take the log of our probability and negate that. And that gives us a positive quantity that, as the decreases, is better. Okay, so higher likelihood. So that gives us this kind of loss function that you see here. And interestingly enough, if you now minimize this and solve for our optimal weights, you actually recover the exact same least squares solution that we had before. The difference is now we're seeing this in a different light. So this is the best model parameters that actually have the best probability of generating our data set. And in addition, we can also get, sorry, that should be, this last derivative should be with respect to sigma squared. I apologize for that. But we can also get kind of what the optimal variance of our model is, in the same process. And that turns out just to be the mean squared error with our data set. And so this is actually really easy for linear problems. It's more complicated for other kinds of problems, but that's kind of also another reason to choose the linear model here. Just so these things work out pretty easily. You don't have to do any kind of gradient descent or some other complicated thing to actually solve for this. You can get an analytical solution. So this is neat. So now we have this kind of generative model. Again, we don't really want to actually generate fake data. Our goal is to make predictions, but now we can do that and understand our uncertainty to some extent in our predictions. So how do we do that? So just sort of thinking out loud, one way you could do this is now that we have the generative model, we've solved for the kind of optimal weights and variance, we can use that to create new fake data sets and then retrain the model and see how the model would have been, what would be the weights if you had trained it on some new fake data. So I'm not suggesting that that's what you actually do, but that is sort of like a way to think about it. You can actually do this analytically on paper without having to actually physically do this. So I'll sort of leave that as an exercise to the student, so to speak, but that's not too challenging. And so the nice thing is that you can basically derive this distribution on our weights. And so what you see here, so on the left, you have basically the kind of the distribution between W0 and W1. Again, this is our linear weights for the linear model. The maximum likelihood estimate is the least squares estimate, and that is going to be the most likely value. That's the center of the distribution there. And one thing that's interesting to see is you can see that it's, if these parameters were sort of uncorrelated, if they weren't dependent on each other, that would just be like a ring of circles, right? But because it's this kind of skewed kind of ellipse pattern, we see that actually, like, if you increase W, you have to increase W1 in general, right? And so that kind of makes sense, right? If you are increasing your intercept, then you have to kind of decrease the slope in order to still kind of fit your data, right? So the other thing we can do is sample that distribution and use those in our model. So if we sample these weights, we can then feed them through our linear model and get new predictions. And so now we see, oh, okay, now we kind of start to understand there's some uncertainty in our predictions as well, because we could have just as easily, if our data had been slightly different, we could have just as easily recovered these models for our best estimate. And so this gives you some kind of predictive variance. So I didn't actually present how to arrive at these equations, but just so you have them, I'm just summarizing here what the actual prediction is and its variance for this maximum likelihood estimate model for just generalized linear model. Again, I skipped all the details. This is kind of easy enough to work out if you want, but here it is. And so now going back to this third order polynomial data, it's interesting to look at what the kind of predicted, the predictions are along with the variance for different polynomial orders. So going from left to right, you have basically a linear model, third order polynomial, and a ninth order polynomial. And now I think you kind of can see the benefit of this sort of way of thinking in terms of generating, having a generative model. And that is, if you look at the third order polynomial, it seems to not be as affected by the noise in your data in terms of extrapolating to farther away from your data, right? So we say that it tends to generalize better to the data. However, the linear model actually has a lot of uncertainty because if you were to sort of re-choose those data points, you might get a large change in the actual parameters for your line. And so that's represented there in the kind of uncertainty around the best fit. For the ninth order polynomial, now you can see the very high uncertainty outside of our data set range. And again, that's sort of going back to how well you generalize. And you can see that if you had small changes in your data, you could get very different results outside of the data set. And so again, this is sort of another way to look at it and gives you some kind of indication that a third order polynomial is probably best here. Any questions so far? Probably lost everybody. I have no idea how much time I have. Okay. I don't see if there's hands or anything. Okay. Okay, so I'm going to keep going, but feel free to stop me if anyone has questions. So I'm going to just very briefly touch on Gaussian processes now. So this is a different type of model, but this is something I've used quite a bit here at NASA. It's actually something I learned here at NASA. So this is somewhat new to me as well. And I think it's kind of an interesting choice of model that probably doesn't get as much attention as something like a neural network. So, and also so you kind of understand the examples later, it's useful to just touch on this. Again, this is not going to be a super in-depth GP intro. In fact, it's 2 slides, but hopefully gives you the kind of flavor of what it's doing. So, what is a Gaussian process? In general, in statistics, processes are essentially random functions. So a Gaussian process is essentially the generalization of a Gaussian distribution for random scalars to random functions. Okay, so what I'm talking about here is on the left, you have a very, I was going to say a very normal plot of a normal distribution, but it's a Gaussian, right? So you have some variable x, and it has a probability distribution that is a Gaussian distribution, which is characterized by some mean, which also happens to be the peak of the distribution, and the variance. Okay, and so you can see that the standard deviation again is the square root of the variance. I normally write the variance as the standard deviation squared, sigma squared. Okay, and likewise, we can think about functions in the same way. So on the right, I have basically the same. So at the top, you can see kind of the way you typically would denote this. So for the Gaussian distribution, we would say x is simulated by, the squiggle, generally red, is simulated by a normal distribution. And then here we would say f of x is simulated by the Gaussian process, which is a function of a mean function, mu of x, and a covariance function, k. And so covariance function essentially tells you how f varies, or covaries, I guess, between two points in your input space. Okay. So, and in the same way, you can essentially sample points from a Gaussian distribution, right? So most of these will be close to the mean. Some of them will be far away. You can also sample functions from a Gaussian process. And so it's really identical. It's just a generalization to a functional space. Okay. So why this is interesting and useful is that you can actually perform regression using this type of sort of mathematical object, I guess. And so the way that works is basically you assume for your model that for any finite set of points, typically these are called index points in sort of Gaussian process literature, but let's say any set of input points that you have, these are going to represent a multivariate Gaussian distribution for the function values. Okay, so in the case that you have 3 points, this is what I've kind of written here. You can evaluate your function f of x. You can evaluate it at x1, x2, and x3. And that vector is simulated by a multivariate normal distribution, which has a mean vector, which is your mean function evaluated at x1, x2, and x3, and this covariance matrix, where each term in the matrix is just the covariance kernel function k evaluated at the corresponding points. Okay, so using basically just sort of standard multivariate Gaussian results, you can actually condition this multivariate distribution on data. So this is where probably I lose everybody, but the idea is that you can actually just kind of write down a new GP that's conditioned on data, where you basically know what the mean and covariance functions look like given your sort of initial assumptions on those. So again, I lost everybody, but the point is that like you can take this and with 0 parameters, so this is actually a non-parametric regression model, you can write down a regression curve. And so the way this would look on the right, if we add one data point, so let's say we evaluate the true function, so that's the solid black curve. We evaluate this at a given data point that I show in red. You can see how basically our model, basically the uncertainty around that data point collapses to 0, and our prediction now starts to get closer to the true function. And as we add more and more data, we start to get better and better predictions of the true function, and our variance around that, around the true function starts to decrease as well. So this is all I really have about Gaussian processes. There's a whole lot more, and I'll include some references at the end if people are interested. But this was really, again, just to give a kind of flavor of how this works without going into all the details. But yeah, hopefully, if anyone has any questions on or general ideas, that would, feel free to ask. But yeah, maybe we can talk about details later if someone's interested. Okay, so I'm done with all the, I guess, boring introduction stuff. So I'm going to move on to kind of examples of where I've sort of used machine learning in a few projects. So the first one I want to talk about is actually an early career initiative project, ECI. So this is something that's actually currently ongoing. It just started this year. Samdutta here at Langley is the PI for this project, but it's a pretty large group of people, and we're basically studying the feasibility of aero capture in order to essentially demonstrate aero capture as a viable alternative to propulsive orbit insertions for gas giants. And so specifically, we're sort of considering Uranus because that's, as you may be aware, that's basically been sort of selected as the next sort of flagship mission, I guess it is. So there's a lot of benefits of aero capture. One is that you can basically get there faster, and you can actually use less propellant to slow down, and so you can basically have a lighter, you have sort of smaller mass, which means you can increase your payload capacity. You can also decrease your cruise time, which is very important, in particular for the type of science missions that would want to go to Uranus. Basically need to get there by a certain date, and that's more and more infeasible as time goes on without aero capture. So this is definitely a promising kind of technology. So my role in this project is the aero heating database lead, and so my job is essentially to take trajectories that the trajectory team and the aero team provide. They basically compute these trajectories to the atmosphere, and I basically have to say, okay, how much heating do we expect on the body of the vehicle? So you can see basically here a kind of summary plot of that analysis. The black curves here represent trajectories. If you're familiar with these kind of, velocity altitude graphs, in this case, velocity free stream or free stream density is on the left, it might look a little weird. Normally you have kind of the altitude goes the other way and you kind of are coming into the atmosphere and then landing. That is something different about aero capture. We just dip into the atmosphere and then dip back out. And we use the atmosphere to slow down. So that's what you're seeing here. And so in order to kind of arrive at this heat map that you can see, I had to basically build a kind of surrogate model. And so that's where sort of machine learning and Gaussian processes come into play for me in this project. So the way I kind of approached this problem was take, I kind of have an atmosphere model, depending on how much you believe the Uranus atmosphere model, but we have an atmosphere model, and it has trajectories sort of passing through the atmosphere, and I kind of know what the state space looks like for the vehicle, and so I can basically sample points in this state space. And in this case, I use something called Latin hypercube sampling, which is just a way to, it's a random sampling technique, but it tries to ensure good coverage of the space. So it's kind of random, but not fully random. So all of the X's there you see are basically conditions that I sampled in the sort of altitude and velocity space. And then using the altitude, we can back out the atmospheric conditions. And so the idea was to sort of cover, in this case, this group of trajectories here. So given those conditions, I could then go off and, basically compute the aero heating environments around the vehicle. In this case, this was done using the LoRa and HARA code here at Langley. And then the sort of interesting part for this talk is really like, how do we then take the data at those sort of discrete points and actually build a map, this sort of heat map that you see. How do we construct this using sort of machine learning surrogate methods? So this is a good time to talk about data set normalization. So I didn't actually mention this during the intro, which I think probably was definitely an oversight, but I have it now. So in general, when you have a kind of any machine learning pipeline, you really want to normalize your data set, and there are different ways to do that. And there are various reasons to do that. Some models, for example, if you're familiar with principal component analysis or PCA, that actually requires that you normalize your data set in this sort of standard way, where you basically subtract the mean of your data away off of all your data points and divide by the standard deviation. And so that is kind of actually baked into the PCA framework. And again, this is going back to Levi's comment at the beginning. That is why machine learning can be hard, is that if you did not know that, your PCA is going to just be terrible. And so that I've seen that happen to people before. So another, I guess, aspect of normalization is sometimes it's also a good place that you can kind of build in your sort of intuition and physics knowledge. So it's always a good idea to ask what you actually know about the data. So there are always going to be possibilities to do essentially dimensionality reduction, feature selection, or feature engineering. For this particular problem, it was kind of important to think about sort of known like engineering correlations or scaling laws that we have. So for example, we're interested in the heat flux on the vehicle. So for these results, I'm just showing four body results. But we know that at least from the Sutton-Graves model, if you're familiar with that, there's this kind of engineering correlation that we have for the maximum or stagnation point sort of convective heating, where it's some sort of constant coefficient K times the square root of the free stream density over the nose radius times the free stream velocity cubed. And so typically you can find values of K for different atmospheres that people have fit. Likewise for the pressure, if you have sort of limit of, I guess, infinite Mach number, you have this sort of Newtonian pressure theory, which tells you that the pressure is the sort of max stagnation pressure is typically kind of proportional somehow to the density times velocity squared. And so just sort of thinking about that and sort of knowing this in the background, right, you can think that, well, maybe I can kind of normalize my data by some generalized Sutton-Graves type fit. All right, so because in general, it's some sort of constant times density raised to a power times velocity raised to a power. And so this is where sort of linear models come back. You may not have initially realized that this can be made linear. If you take the log of both sides, then this is obviously a linear problem in the parameters, right? And so using our simple linear fit, we can actually construct models given our data for these coefficients for generalized Sutton-Graves, which is what I've done. And then if I take that and normalize every case by this value for the pressure, the convective heat flux, and the shear stress, and then plot basically the results for all the different conditions, you get this plot on the left. So you can see that by normalizing in this kind of way, which is based on our kind of physical intuition of the problem, we've actually sort of done dimensionality reduction, right? We basically all of these curves essentially collapse onto kind of the same profile, and then we can fit these profiles as using a Gaussian process. So we can take into account the kind of mean value of these profiles and their variance, and very easily fit a GP. And so if we take basically those two concepts together, this sort of linear model normalization and a Gaussian process, we can then create what's called this regression plot on the right here. So this is a very typical way of looking at how well your model does, even on very high dimensional problems. It's always going to be 2D, which is what I like about these types of plots. Essentially, on the x-axis here, you would plot your sort of truth data. So in this case, it's the sort of heat fluxes obtained from CFD at all the body points for all the conditions. So on the y-axis, you put what your model would predict. And so that's basically what the blue scatter points are there. And just for reference, I put kind of what the line would be for an exact match, and the shaded region is just plus or minus 10%. around that. So you can see that this model, while pretty simple, manages to do really good enough job because, you probably don't trust our predictions more than plus or minus 10% anyway, so that's probably good enough to call it a day. So that was one example. So another kind of example along the same idea of generating these sort of databases or surrogate modeling is some work I did previously for another early career initiative. So this was called AeroFusion. This was a pretty neat project where basically the goal was to try and answer the question of, okay, whenever we build aero databases, in this case, this is for Orion, you have literally nearly 2 decades of wind tunnel experiments on different geometries and a ton of CFD solutions on different codes under different modeling assumptions and so forth, right? And so how do you combine all of this information together? This is typically called data fusion, and put them together in a way that you can construct a single, in this case, aerodynamic database, right? So given the vehicle state, so the Mach number, the angle of attack, side slip, and Reynolds number, et cetera, how can I get out the lift, drag, and pitching moment coefficients, for example? All right, so that's what an aero database is. And this is typically used throughout the rest of the sort of design and analysis stages when you're designing and flying a vehicle. So, it's used in trajectory simulations, it gets used in GNC algorithm development, and basically as those various analyses mature, they kind of filter back into saying, oh, well, actually we need to, get some more data at this condition with this geometry, whatever. And so this tends to be a kind of iterative process. And on top of that, the noise, the data is quite noisy in general, at least in our experience. And you may have varying degrees of fidelity to the actual flight vehicle. And so as I mentioned, data gets continuously updated. And the various wind tunnel models essentially approximate the actual vehicle geometry and its roughness. Typically the roughness is not really known ahead of time. This is something that actually, for the heat shield, for example, is going to change throughout the flight. That's not something you can really kind of deal with very well in various wind tunnels. And wind tunnels don't always reproduce flight conditions. On the other hand, CFD might reproduce the flight condition, but it's not really as accurate, perhaps, as a wind tunnel model, right? So, sorry. And so the sort of current state of the practice is something that we in the CCI essentially coined UQ by inspection. So generally, how the Orion database is constructed is you basically fit some kind of model to what you think the nominal sort of geometry is, the nominal roughness is. In this case, they use essentially what the symmetric geometry looked like, which is not the real geometry, and a smooth wall conditions, and that's what they use to sort of fit their model. And then they basically take all the other data and see how far off it is, and then that's what they use as their kind of uncertainty. And so they kind of have a way of building up different uncertainties by incorporating different parts, different aspects of this uncertainty. What we would really like, if wishing made it so, we would really like to just kind of learn what a surrogate conditional probability distribution would be given all the data sources. So what I mean is we want something like this, where we have this conditional probability of, let's say pitching moment coefficient. How likely is the pitching moment coefficient given the state of the vehicle, in this case, X. And so it's important to kind of realize that here the surrogate model is stochastic in nature, but it's not random, right? So you would imagine that functions going through this space are still smooth. So there is some regularity with respect to your input X, but it's random in the sense that you can have different functions are just as likely. Hopefully that makes sense. So the sort of results I'll show here are basically an example from the Orion, this is the National Transonic Facility testing that a couple of the tests that were done here at Langley. We have basically four different campaigns that were performed, or four different, I guess, groups of tests. So we're going to take three of them and use that to train our model. And those three are basically nominal, basically the axisymmetric vehicle geometry with a smooth wall. We have another model that basically has kind of a sand grit on it, and that's sort of to help model roughness effects. And then an additional geometry that's based on, it's closer to the real geometry of the vehicle. You can see the pictures there. And so but it's smooth. So the idea is to try and capture asymmetry effects. We're taking as flight data just additional wind tunnel data, but in practice you would want to use actual flight data, where it's the correct shape and has basically fencing and roughness applied to the outer mold line in order to kind of approximate what the heat shield might look like after it has ablated a bit. There's just some examples here on the right of the actual kind of raw data. So you can see how noisy the real data is, right? This has all been normalized, so you're not seeing the real kind of coefficient values, but you can still get a sense of how noisy these things can be. And again, it's for different, and you can also sort of see that there is a clear effect of roughness and asymmetry on the data, right? So the black dots here, for example, are kind of nominal. So we took that data and essentially bend it just to kind of reduce the number of data points we have. And so you can see the sort of the bending process in the bottom there, but that's not super important. So I mentioned GPs. There's a whole literature on taking GPs and basically doing multi-fidelity Gaussian processes where you basically have a hierarchy of GPs that you stack on top of each other and you train one at a time to get your ultimate prediction. The problem with that is since it's kind of hierarchical, you're assuming that you have some kind of truth. You have some like perfect high fidelity data that you want to use, and you're basically fitting different levels of fidelity data in kind of climbing the ladder up to this level. Unfortunately, the real world doesn't really have that because, for example, if you don't have the actual flight data, there's no sort of truth, right? If you're in the process of designing a vehicle, you don't have flight data yet. So there is no sort of truth, and so that's kind of hard to pinpoint. Instead, it's a lot easier, I think, to categorize sort of nominal and off-nominal data. And so in that spirit, we basically developed a kind of new multi-fidelity scheme called multi-hierarchy Gaussian process regression, where we basically combine Gaussian processes in such a way that we don't rely on truth data. Instead, we try and model offsets from some sort of nominal data set, and we basically linearly combine these together. So again, kind of linear modeling comes back because you essentially will need that to estimate what these weights are in the model. And again, not really trying to like show all the details here, but this is just to kind of give you an idea that you can always make these things much more complex, which is what we did here. So looking at the actual sort of trained distributions that we came up with, you can see, again, the data. So this is basically for drag and pitching moment coefficients, again, normalized versus angle of attack. You can see the data, and then the shaded regions are essentially the probability distribution. These are really slices because this was if I remember correctly, this is a three-dimensional space, so it's at different Mach numbers and Reynolds numbers. So for one Reynolds number and three different Mach numbers, you're seeing basically slices in this probability distribution space. And so the black, red, and blue data and curves are all the sort of given data that we trained on. And the green data set is what we called flight, if you remember a couple slides ago. That's something that the model did not actually see, but we were trying to essentially predict the probability of that given our other data sets. And so sort of the first thing you can notice is that there's pretty good agreement with all the data that is quite noisy. And then this actual sort of simulated flight data that we were trying to reproduce is actually reproduced fairly well, so considering that there are going to be some sort of effects that are not accounted for by the roughness data or the asymmetry data. And so I think this is still a pretty interesting result. Another cool thing about Gaussian processes that just sort of fall out of the whole GP framework is this notion of out-of-distribution uncertainty. So if you remember when I was talking about the kind of generalization overfitting with polynomials, if you have a seventh order polynomial, you just have this like crazy uncertainty once you leave your data set space. GPs sort of have a similar notion in that the variance of the GP increases the farther you get from your data. And so that's also a great indication to say, oh, I need to have more data in this area, if that is sort of part of the state space that you expect to actually see during flight. Okay, so lastly, probably should wrap up pretty fast. So I will just quickly mention some work I did on physics-informed neural networks. Again, I didn't talk about neural networks before, but the idea here is essentially to take to kind of this essentially replaces conventional CFD, where the idea is instead of basically discretizing time and space in the sort of classical discretization approaches, you actually want to basically just approximate your solution as a neural network, and then apply the PDEs as a regularization in the loss function. And this essentially converts your system of PDEs into a large optimization problem, as opposed to a large system of ODEs in the classical discretization case. There's a lot of reasons for doing that. Let me just skip ahead. I'm going to skip over what neural network is because, again, I think people at least notionally have some idea of what that is, if not the details. And so just to kind of give an idea of how you actually sort of train neural networks to solve equations, in this case PDEs, these are sort of the steps. So if you consider you have some kind of general PDE, so this is some PDE, which I call like F is sort of PDE operator, and so you can represent this as some operator on your input equals 0 on the right-hand side, and you have some boundary conditions as well. If we just build a neural network that we want to approximate the solution of this PDE, we can do that. And then if we distribute points in the space of the space of interest, so the domain and boundary, I guess, of interest of what we're trying to solve, then we can evaluate our neural network on those points using the PDE. So we can basically use the PDE itself as our loss function, where we've plugged in the neural network. So we essentially take all the derivatives of the neural network that you need to represent your PDE, as well as the boundary conditions. And so you can kind of see a little schematic of that. And so the cool thing is you don't need a mesh for this. You just can randomly throw points at the problem and basically minimize this loss function that's based on your PDE and get a neural network at the end that represents the solution. So we did this for the Navier-Stokes equations. This is non-reacting, thermal equilibrium, but basically just trying to understand what heating would be predicted on some simple problems using this. And we compared it to some LoRa solutions for a flat plate in this case. So I have some sort of the parameters of the architecture, the neural network architecture and stuff there on the left, and some of the training. But essentially, you can see on the right there, basically the LoRa solution and the physics-informed neural network solution on the right. And just visually, you can see that they're like nearly identical. And what was really interesting to see is that using that, actually, first off, the sort of shock was actually better resolved by the neural network solution. Again, because it's not really discretizing the space, so it actually has exact analytical derivatives, and so that's one nice property. But also we see that the boundary layer is quite well resolved. and in particular, the heat flux on the wall is basically perfectly matching the LoRa heat flux. And I'll also mention that, in order to compute this heat flux, right, you need the sort of gradient of the temperature, and this can be done exactly with the neural network, as opposed to basically having to do some kind of, finite difference or something from the CFD solution. And so it was kind of neat to see that these line up. Okay, so I'm going to end here. I'll leave this up. This is not a non-exhaustive list of resources for people interested in finding other information. These are all books that I've at least skimmed. I won't say I've read all these, but the deep learning book is a very good resource if anyone's interested in doing neural networks and deep learning. And the Gaussian process for machine learning book is really the kind of classic text on that if you're interested. And a lot of the slides on the linear model that I had were kind of loosely following some chapters in this first course in machine learning book. So feel free if you want a kind of much better description and introduction, I would just go directly to the source. Yeah, so I think I'll end there, and if anyone has any questions, I'd be happy to answer them. Thanks. Anybody need water or go to sleep or something? Yeah.
It's hitting the chat, but Jeff might have some in the room. Jeff, do you have any questions?
Yeah, I think we have one question in the room here.
Firstly, thank you for the great presentation. And what I was wondering is, your PIN approach was something very similar what I've been considering to do. So I was wondering if you ever check the surface quantities on the PIN predictions on the flat plate case, for example, surface pressure distribution or something like that, rather than the flow field itself.
Yeah, so like the heat flux, for example, that was the surface heat flux. Sorry, I'll go back to playing this. So this bottom right figure is the surface heat flux. I don't think this was kind of a while ago. I don't actually remember if I looked at other stuff, but this is the slide I could find back. So this is what made it into the presentation.
Okay, thank you.
Any other questions, Jeff, on your end?
Hi, so I was interested if you have any ideas on resources to, I'm pretty familiar with machine learning, but I'm curious about PINs in particular, physics-informed neural networks. Curious if you have any suggestions on resources to learn about those.
Yeah, so the short answer, which may sound like I'm just tooting my own horn here, is that I have another lecture on that. But the real answer is that at the end of that, there are also resources as well. So I can direct you to that. Yeah, I will put a link to, there's a GitHub repo with all that. I'll put that in the chat after this.
Thank you.
Sure.
Anybody else? Jeff, are you good?
If there's no other questions, I'm going to throw in at JB if I can. JB, if you don't mind going back to the arrow capture example that you were doing, I'm curious. So, did you try playing with having a free stream dependence on the linear proportionality coefficient? So at C theta, I think it looks like those are constant across your domain, right? Or did you play around with any kind of functional dependence on rho infinity and v infinity there?
So the functional dependence, I guess, is the kind of way I'm normalizing the data. Mm-hmm. So it's just like a power of the density and velocity.
Right. So I guess what I'm getting at is, so that C theta, we've seen that tends to vary across the domain of interest based on basically because that encapsulates changes in like the physics of the problem, whether there's certain chemistry processes or service processes going on. So I was just curious if like you played with any of that to see if that improved the Gaussian process regression.
So I guess you're referring to like the recent like paper from Carol and
That's right.
Brandis. Yeah. So I haven't done anything like that for this. I think in our case, we actually kind of benefit from actually a fairly limited trajectory space.
Mm-hmm.
So we don't go as deep in the atmosphere as you would if you were actually sort of sending a probe in. And so it was like good enough essentially with just doing this. So I think because we don't have as large of a state space as I think what they covered in that paper, we didn't really need to go that far. So I mean, you can see essentially the results here. Basically, it collapse. All of the data points essentially collapse onto more or less the same kind of profile on the body. And that's just because this is normalized by that kind of maximum, which is predicted by this Sutton-Graves model. So I think for this particular data set that works. I will say I tried to do this for radiative heating. We don't really seem to get a lot of radiative heating for these conditions, which is kind of well known, but we are looking at much faster entries depending on the kind of sort of interspace trajectory that you actually take to get there. And so if you go to higher, I can show here, so like this was going up to less than 27 kilometers a second for the entry conditions, but if you go up to like 30, radiation starts to become like on the same, it's like 50-50 with convective. And the radiative heating is a kind of lot harder to model with this simple Sutton-Graves model, which again is not, which is also kind of well known, but I did try it just to see if it would work, and it doesn't really work. So we'll have to do something a little more intelligent, probably.
Very cool. Thank you, JB.
All right, anything else? Well, thanks, JB. I agree with your student that some of it was pretty straightforward and some of it was a little hard to follow. But very interesting topic. Really appreciate it. And just to close here, wanted to make sure that people realize that Tuesday's seminar is canceled, and Thursday will be our last one, and it should be a pretty exciting talk. It's about the Lofted flight that just happened this past fall. So thanks, everyone, and have a good evening.